Okay, so we should be recording right now. Sorry for this slip. Okay, so let me go over first a few administrative slides about what this class is about, like how we're going to do stuff this quarter, the textbook, homeworks, etc. So welcome to the class. So the course objectives of the Intro to Cryptography. So basically, my aim for the class is to teach you about what the standard cryptographic tools provide, so that you can use them appropriately, and you can understand what guarantees they provide. And also you can understand and you can become attuned to what the limits of these security guarantees are. So you know that if you once you understand what the encryption provides, or signature or message authentication or what have you, you will also see that it doesn't provide certain other things that perhaps intuitively you might think that they do, and that is also useful knowledge, right? So you shouldn't use cryptographic building blocks in ways that actually they do not provide guarantees for, or such users might lead, and often does lead to bugs in systems. And sort of at a higher level, I don't want this class to be like a cookbook, as in encryption does this, authentication does this, signatures do that, etc. But rather see it as examples of certain common methodology functioning in operation, and this methodology would consist of stating what the security properties are and arguing whether they are or are not achieved. And the language, the methodology, the certain formalisms that this requires are a little bit of, it's a kind of a steep slope. It's at first it's kind of like a lot of formalism, a lot of conventions, that it's a little bit like drinking from a fountain. Then you will start seeing patterns that actually the same way of stating things reappears. And now, most of you will not use this class in order to continue like research in cryptography and be able to use this methodology to write proofs and to create constructions and to argue about the security. So in that sense, the class gives you certain esoteric information that you will not, in many cases will not use. On the other hand, the practice of stating this and the reasoning about this, I believe, does give you some useful stuff. So it basically attunes you to what in the design might switch from secure to insecure, might basically either help the construction or destroy it. And that practice will, first of all, teach you to be careful modifying anything in crypto systems. Second, it will maybe teach you to be careful in understanding that whenever the security properties are stated in certain contexts, they might not carry into another, because that will be precisely the nature of the bread and butter that you will see in this class. That something that worked in some security context completely fails in another, and why that is. So this will be visible once you start arguing security, and instead you'll be able to like learn this methodology. Otherwise, it's hard to see anything. And I believe that being able to see these things is it's a very fundamental thing that we want to teach in this class. Just like be careful with this zoo of cryptographic objects that cryptography can provide. And even if you cannot do proof for some variant, at least be aware that changing stuff is dangerous, and you need to recheck this and maybe consult someone. Okay, and that kind of stuff is valuable in practice whenever you use these techniques for in any context, really. So and well, I believe it's a very beautiful field with lots of completely counterintuitive things that turn out to be possible, and with very surprising and elegant results. And it's incredibly active and ongoing, and there's always new horizons that open for cryptography to attack and to move into. And it's a fast changing landscape with attacks on certain cryptographic assumptions we've heard so far, designs of new ones that are aimed to fight new computational models like quantum computing, and new application domains feasible because of the general improvement in in computer infrastructure, right? Like speed of hardware, software, etc. But also huge gains that are possible due to research and things that we knew only that we had feasibility results for a decade or two ago. Now with intense research turn out to be much closer to practice than thought that was thought possible quite recently. Okay, some administrative stuff. So here is obviously we are on Zoom, so you know how to reach me through email, etc. The room number doesn't matter because I mean that's for future. That's where my office is at Bren Hall. We don't have a TA. The class is too small. The lectures will be 2 p.m. on Zoom on Monday, Wednesday. I will record them as I'm recording now, and I will post them. So you can, whenever you need to skip a class for some whatever reason, you can check a lecture after. And I will have office hours weekly. Maybe Tuesday, Thursday makes most sense. Perhaps somewhere in the afternoon. I will post those shortly. The prerequisite for the class. So there's no formal prerequisites, really. I guess there are some in the catalog, but we will use algorithmic vocabulary. So it will, familiarity with algorithms is definitely a plus. We'll use computational theory vocabularies, and something is, polynomial time or exponential time, or we will actually use the notion of reduction that you might have not encountered unless you're a theory person ever since you took some sort of intro to computability and a theory of computation class, perhaps years ago. But a notion of reduction between two problems is actually a completely key notion for cryptography, because being able to show that solving one problem implies solving another is exactly like what is happening in the security proof. That if somebody can attack some construction, the only way they can do so, if that translates to attacking an underlying assumption, like factoring assumption or lattice or whatever arithmetic assumption is behind a crypto system. So reductions are like all we do to argue security of systems, of cryptographic constructions. So something that is like very esoteric for most people, it's actually a fundamental thing for us. Discrete math, well, obviously, like you see, precision and logical clarity is of utmost importance in this class. Like if you miss for all and you interpret, and there exists, and you miss the order of quantifiers that says, that for all ciphertext there exists a key versus for all keys there exists a ciphertext. These are completely different statements, and if you're shaky in understanding such statements, okay, you will suffer. But this is basically discrete math that any CS person should know. So it's not like anything super special, right? And the basic probability, right? We will not use sophisticated probabilistic tools. We will not, this is not like the stuff that, like some serious statistics that happens in machine learning. We'll have very crude statistical concepts, okay? But you still need to know what a random variable is. And you should know what it says, when a probability, conditional probability, what that means. Okay, like when you fix certain variables and you're asking what is the distribution of some hidden stuff subject to these constraints. And another thing that we use all the time is modular math. So this is normally taught in a discrete math class, like that, what's the modular arithmetic. So, it will get, of course, a little more sophisticated than that, but this is the basic ground on which we build. Here's the textbook. I email you this link. Introduction to Modern Cryptography by Katz and Lindell. On Amazon, you can get an electronic version of this, and you can also get it permanently, or you can rent it. The latter is cheaper, but the former gives you a permanent reference. So it just depends, I guess. Unfortunately, you have to decide now, I think. I don't know if Amazon has like some sort of scheme that you can rent it and then purchase if you change the decision at a discount. There will be a few homeworks in this class, perhaps 5, perhaps 6. Your grade will be determined by these homeworks. And I will post them, of course, and post solutions, and I'll post lecture slides, and I will post Zoom, the video. And I guess everybody is registered for the class, because like in this case, you cannot just come into a room without having emailed me or being registered. I will send a link when the homework is up for a Gradescope. That's how you will upload your solved homeworks. And I would like you to, if you team up with someone that you're very much welcome to, for fairness, maybe don't do that in a group larger than just a pair. And be clear in crediting. So if you work with someone on any problem, write the names on the top of that unappropriate page, right? And if you use some internet resource, some other lecture notes, some, there's many people who teach cryptography from the same textbook. So, you should not search for verbatim solutions to what I give you as a homework problem, but it might happen that as you look at other nodes, you basically see a solution to some problem, or like a big hint. If that happens, write that. So state what you're basing your solution on, where you saw it, right? Because otherwise it's cheating. And if something somehow tempted you and you could not, and basically you saw the solutions, by all means, say that. Because look, if you don't, it's a violation of academic honesty, and it's like all hell breaks loose, right? Basically, I have no way to tell like whether you did it because it was a mistake or whatever. You did it, you didn't say it, it's kind of game over. So don't do it. Like, there's no reason to do it. Just, it's also a graduate class, right? So, it's not a elementary school. It's not a really a chase. Okay, this is academia. This is like about you learning something and not you getting B plus versus A minus. There's nothing that is going to happen with you getting B plus or A minus. No one cares, I think, really. So, but on the other hand, if you are interested in this stuff, of course, I will like see, and there's other faculty who works on related issues, and this stuff is going to be, maybe important in your research, right, or in your professional life. In any event, being honest and maintaining, academic and honesty is much more important than whether you get some problem on the homework set done, right? And the consequence of failing to maintain academic honesty standards versus consequences of not doing some homework problem, they're like night and day. They're incomparable. So that's just like, so you all know like where we are standing, right? And what you sort of expect it to do. If there is any questions on that, by all means, let me know early. And I'm focusing on this because unfortunately it is an issue, and we do get occasional students who messes this up, and it's like just sad to see and completely unnecessary, and I would like just to be avoided, and very, very unpleasant, for everybody involved. All right, me. So that's why I don't want you to do it, because I hate dealing with this. All right, and I hate to see people being, in that situation. All right. A very important resource, a Piazza site for the class, where you can have, this will be a primary way of communication. So I will be posting stuff on Piazza, and it would sometimes generate an email to all of you. So this is the most important thing. You have to sign up for there is a piano sounds, hopefully not too bad. If they get too bad, then let me know, and I will tell people in the other room to stop. Okay. So yeah, maybe this is a good moment to take some questions before we jump into the topics. Maybe it's a good question for me to tell people in the other room to stop banging on the piano. Hold on a sec. Zoshko, I'm on the lecture, so like don't bang on the piano. Sorry. Okay. Sorry about that. So in the meantime, somebody has any question? Okay. this is not the last time you can ask questions. So let's move on. All right, good. Okay, we're jumping into chapter 1 of the textbook, like a general philosophy of this class. That's this first part. Okay. Hey, since I'm a cryptographer, I see cryptography everywhere. So if you have a hammer, everything is a nail. But secure communication is all over the place, right? Web, any other form of secure IP or TCP communication, also wireless, many standards there. Disk encryption, another obvious case, and these are cases of sort of point-to-point communication, or in this case, like a communication of my previous self with my future self, the guy who wrote down an encrypted file and the same person who read it later. There's also protocols that parties engage in, like, for example, establishing a key used for secure communication or for disk encryption. We call those key agreements or key exchange. Authentication of users, it's separate really from secure communication or any of these. And there's many, many more. So as you will see, I mean, the general mantra that we repeat to ourselves and to students and anybody who listens is that, as we do more and more online, security, privacy, reliability of this electronic infrastructure is only grows in importance. So here's a basic crypto application, right? So secure web communication on the web. In here, you have a sort of asymmetric situation where you have a web user communicating through a browser and a web server, right? And then there's this secure HTTPS, that the fact whether or not you have engaged in it is communicated to you by the browser through some sort of like a little lock mechanism, the common interface, to let people know that they have just entered HTTPS rather than just HTTP. Well, it's not exactly a session, but whatever. Okay, it's not a session. So secure, not a session. Maybe that's good enough. What does HTTPS do? Well, intuitively, it tries to protect the traffic between Alice and Bob, in that it will, any eavesdropping on this channel is useless, does not leak any information about what these people send to each other, and also prevents tampering. So modifications of the stuff can at best lead to denial of service, but sort of nothing else, right? And clearly, if you can interfere with this communication, you can do a denial of service. So that's unavoidable. By the way, can you really stop people from learning anything from this traffic? Not exactly, because they can count. If somebody sits here, then at least they can see how many messages go through and what are their sizes. And that can be actually that can leak a lot of information. We don't deal with this in this class, except at some very obscure moments. But it's just something FYI, right? So HTTPS technically is that HTTP, right? The browser language goes over SSL instead of TCP. So SSL is secure socket layers, but what is this? So SSL used to be called TLS, the transport layer security, so like a secure version of TCP. And it has two parts: a handshake protocol, which is a key agreement. so a key exchange. So two parties, Alice and Bob, who don't have long-term keys in common, and therefore don't have any key material that they can use to encrypt and authenticate messages. First of all, have to establish that. That is called key exchange. Also, it's another thing that should happen is not just exchanging keys, but also entity authentication. So, okay, I have established a key, but who with? Who is this Bob on the other side? And conversely, from Bob's point, who is Alice? Even though this is the first part, we will do this later because this part is more complex. Well, okay, essentially it will reuse some elements from here. So now, once key is established, what happens then? Well, you transmit data using this shared secret key that you just established, right? The goal is confidentiality of communication and integrity of communication, right? So prevent eavesdropping and prevent interference. And this is the first part of the class. So if you look at the calendar textbook, also it's basically first big chunk is all symmetric crypto, all about you have a key. Alice and Bob have a key in common. How do they use those keys to securely to protect confidentiality and integrity of communication between them? This is, well, not really either easier or harder. This is hellishly hard when you dig deep enough. But understanding this part will give us certain tools, and it will give us some basically the concepts they will see reused here. And this part has difficulties of its, some difficulties. Okay, in particular, we'll use different numerical settings to accomplish these things. So that's why we do this part first, because of reuse of certain concepts, as you will see. But basically, in some sense, this slide captures like 85% of what's happening in this class. This captures like a lot of what you need of symmetric crypto, and this captures a lot of what you need of public key cryptography. And but I'll put a sales pitch for a lot of other things that crypto can do, even though Lendl, in a way, and what we do in this class is really kind of creating this foundation to understand this part. And also, it is like it's the only way to use cryptography in a more sophisticated way is to first of all understand how it assures this basic stuff. The bread and butter of this cryptography is the symmetric encryption, and even more a symmetric cipher. You'll see that the two are not exactly equivalent. Alice and Bob share a key, and there's two algorithms: encrypt and decrypt. Encryption takes a key and a plain text message and outputs a ciphertext. This is the application is that you send out the ciphertext in the wild world, and perhaps it's intercepted by an attacker. That's why you encrypt, because you are precisely concerned with the ciphertext being overheard. But if a ciphertext reaches your intended counterparty, Bob, the decryption algorithm on the same key will decipher it and return a plain text back. The encryption algorithm D and E are known, they're public. The only thing that is secret is the key. So it's the first principle of of cryptography that we don't care about security by obscurity. So all algorithms are public. only random variables can possibly be secret. Now, so this is a very basic scenario, right? You have a shared key, Alice encrypts, Bob decrypts. But even there is lots of possible forks as you study what it is that you want and what is it that you can achieve. So the basic setting is the key is used only once. Encrypt a single message. For example, encrypt an email. And then I don't need a key because I created the key for, in some key exchange algorithm. And now that I created it, I can use it to encrypt a message, and I'm done. It is a simpler case, but it's already rich enough to look into in more detail how it's achieved. And we'll study this one first. This is not what in practice you need most of the time. This is what you need most of the time. So you establish a key, and now you can use it for many messages, right? Like in this HTTPS example, where I had a handshake first, SSL handshake first, the Alice and Bob browser and server established the key, and now they can use it for any number of HTTP messages. They don't have to reestablish a new key every time they have an HTTP message to send. So this is a case of multi-use key, and obviously we'll study this next, right? So we'll first understand how this one works, and then we'll upgrade. And we'll see that certain things here do not work, and that this upgrade is non-trivial, and yet it can be done and must be done. So this is the crypto core, if you speak, if you will. Establishment of a secret key between two entities that communicate over public channels, and an attacker can interfere. And yet, Alice and Bob, at the end of this, are going to output a key that will be just as good as random from the attacker's point of view. Okay, that's the goal of the key exchange. And then once they have the key, how to make it like what does it mean, secure channel, where listening here and interfering are useless, right? So if you're a web browser in your room and this is a web server somewhere far away, there could be many bad people in between, and yet they can do you no harm, or the best they can do is a denial of service. And unfortunately, to count messages. And also, unfortunately, in many cases, they know who is communicating with whom, which is already problematic enough. Okay, so Bob, here is what we would like crypto to give us as well. There is a server and a user. How about a user who communicates with the server but does not authenticate as Alice? So server does not know who we just talked to. And yet the algorithm, and I'll give you a hint, cryptographic algorithm that Bob will perform here, will assure Alice that the server let Alice retrieve, for example, her file and her file only. And yet the server didn't learn who Alice was. In particular, the server didn't notice which file was retrieved. Okay, so I hope you get the sense that this is weird and this is seems like a hard to achieve. and yet it can be achieved. Okay, this is called private information retrieval. And if you sort of change the terms a little bit, which basically like whether Alice and Bob can have a shared state, it's also called oblivious random access memory. Bob can be thought of as a big memory, and it's an access of a memory to retrieve a certain file indexed by a proper index. And Bob is oblivious as to what was being retrieved. Okay. There is, in a sense, more than cryptography that goes in this. So these are beautiful algorithms which actually make sense to talk even without cryptography, but cryptography can helps in achieving them efficiently. So more generally, this was an example of an outsourcing of a computation. The particular computation that is being outsourced is a kind of very primitive one. What is being outsourced is simply an index and a retrieval. This is not really thought of as computation for most people, like retrieving a value from a memory. What kind of computation is that, right? Like a very, very basic one. But if memory is implemented in a complex way, like for example, it's a sorted list, and when you retrieve, you actually need to do binary search or search by a hash table, then it actually is a computation, right? Where you can generalize it. Let's say that this is a database service, right? And Alice has a search query. Can she send the search query encrypted in some way so that the web service, the database service, can process its algorithm on a ciphertext and output a correct result, but in the form of a ciphertext, which only Alice will be able to decrypt. So the key that is used here and here is Alice's key. And the web service cannot correlate these things. Basically, it gets ciphertext, it processes on ciphertext, and ciphertext is the only thing it sees on the output. And yet functionality was assured, right? So this is a privately outsourcing database computation. You can think of all sorts of other computation, like, these are some genotype, and you want to check whether the genes encrypted here are correlated with some sort of disease vectors or some other whatever, right? Like, and then many examples where you might want to, where it would benefit society, everybody at large, if they could perform computation with privacy guarantees. And another cryptographic sort of tool that is not part of this: establish a key, use the key to securely communicate, bread and butter of cryptographic applications, zero knowledge proof. So here is a particular example. So this is a product of two primes is an RSA public key of an RSA crypto system. Let's say Bob knows Alice's public key, but Alice knows her private key, the factorization of this RSA key, of this RSA modulus. And Alice would like to convince the server that she is the owner of the private key corresponding to this public key. In other words, that she knows the factors of this RSA modulus. A zero knowledge proof is a cryptographic protocol that allows for the following. If the prover knows what we call a witness for the statement, so she does know the secret factors that multiply into this, she can convince Bob of it. If she, in a way that is sound, in other words, if she doesn't have these, or they don't even exist, for example, n is a prime number, so there is no such factorization, or it's a product of 3 primes rather than 2, then this proof will fail. So Bob will reject. And so far this can be accomplished trivially. Alice just sends the P's and Q's, and Bob just verifies them. But here's the non-trivial property: zero knowledge. The only thing that Alice conveys in this is that the statement is true and nothing else. In particular, nothing else about P and Q is leaked. The only thing that Bob learns is that they exist. But it is no wiser after talking to Alice. Let's say that he wanted to search for P and Q, because these are Alice's private keys. So if he finds them, he will be able to impersonate Alice. Having witnessed a zero knowledge proof gives him no help in the search problem. In fact, gives him no help in any problem. Like it is of no value. Zero knowledge. It conveys no information except the statement is true. It's a counterintuitive property. It doesn't seem easy. Like, how do you conceptualize what's happening and how do you achieve it? And well, unfortunately, like if we are lucky and go through stuff fast enough, then we will only see it at the end of the class. But there is a cryptography part 2 that I teach at UCI, and that is basically the both of these are like the beautiful stuff that we cover there. And here is the third one, secure computation. So look, there is many things in where that can be done if you have trusted computing. If you have trusted computing nodes, okay. For example, election. So election here simplified to some binary election where people's votes are just 0 and 1, and an election is the computation it performs is just taking majority, right? So is there more ones than zeros? That's the win. Then the winner is 1, 0 otherwise. Another example, auction. So these inputs are prices, and you want to compute the max, or perhaps the second max, or perhaps other auction, the beautiful game theory stuff for like how to structure this in a way that would be most productive. But just takes the simple thing, maximum of the bids, and then which one contributed the maximum, right? More generally, these are some functions of inputs. For elections, majority; for auctions, a max. And people have some inputs, and then what you want is to compute this function on those inputs. And if you have a trusted computing node, well, then everybody could just give the input to that node. The node would compute f and send the value out. What a secure computation asks is, could you do the same without the trusted authority? Because what can the trusted authority do? First of all, it learns the exact input of everyone. Okay, in elections, might not be a good thing. In bidding, it might not be a good thing. Maybe I want to have private auctions. Maybe because these are private auctions, they actually encourage people to participate more. So I would gain if I had private auctions. It's not that being nice. It's actually maximizing your own outcomes by facilitating privacy protected computation. But if it's not, and the second thing is that this trusted authority, quote unquote, can manipulate results, right? And even if there were some trusted parties, the question is that software and hardware is vulnerable. So even if I trust UCI to preserve whatever information for me, perhaps UCI will be attacked, and all its good intentions will not be so useful. So what can be done without a trusted authority? Well, what if these parties communicate among one another? They follow some cryptographic protocol, intuitively encrypt these inputs, and then run the code of F on the encrypted inputs. Okay, and then somehow they also decrypt this joint output. If that was possible, then you could do away with the trusted authority assumption. That's called secure multi-party computation. And it's possible too, and actually feasible in practice because of ongoing cryptographic and security beautiful work. But that too is a kind of second layer application that we will talk in the Crypto Part 2 class. So what is cryptography? Okay, it's a mix of engineering and science. So it's engineering because there's engineering concerns, and there's engineering sort of intuition that you need to understand what's important and what's not, and what kind of solution would be really useful and what kind of solution is less useful, really. And also there is engineering in the way that you construct these things. But at the same time, it's science too, because you need clear understanding of a machinery to be able to analyze and to sift good stuff from the bad stuff. And what is this machinery? It's on this slide. So we need to state clearly what the threat model is. So in other words, what are the resources that adversary sees? Does he sees ciphertexts that are outputs of encryptions of random messages, or messages that come from certain distribution, or perhaps even simply attacker decides what these messages are, and perhaps it decides in an active way. But so seeing a ciphertext, you can decide what the next message you encrypt will be. And what is the adversary's goal? Is it decrypting a message, or just deciding whether a ciphertext is more likely to be an encryption of message 1 versus message 2? The second goal is easier in a way, right? The job is restricted. There's only 2 possible messages, and I don't need to be perhaps 100% right. Maybe if I guess, if my guesses are correlated with whether or not the encrypted message was really M0 or M1, that's good enough. So stating what that is, what the goal is precisely, is the second part of this. Now, of course, propose some construction, right? Like look at some, here's an algorithm that we hope to achieve security, and hopefully it's efficient too. And now prove that that an attack against the specific construction either cannot exist unconditionally. So it just such machine cannot exist. We know that there are some problems that cannot be solved by any algorithm. So information theoretically, I can say with certainty that guessing a random 100-bit string happens only with probability 2 to the minus 100. I don't need any assumptions for this. But often enough, we will need assumptions like hardness of factoring, hardness of discrete logarithm, and you will see others. And so the argument will be that if there is that an attacker, if an attack that has certain capabilities and efficiently or in a feasible time achieves a certain specified goal against a specified construction, then that can only happen if that algorithm can be converted, and here the proper technical term is reduced, to solving some hard problem like discrete logarithm factoring, etc. So, for example, that forging certain standard signatures in some standard signature algorithm is only possible if you break the factoring assumption. Okay. We will see this way of reasoning soon enough, although not in the first week. Okay, maybe by the second week. Okay, so cryptography is a basic for computer network security. It gives you all these bread and butter tools: encryption, authentication, message confidentiality, message integrity, and key agreement, and so forth. But it's also an amazing tool that can create very strange things, which would be and do prove themselves useful, and perhaps will be useful in the future because they basically enable privacy protected computation that is otherwise impossible. But also, it is not a security solution to all security problems, right? We cannot prevent software bugs. We cannot prevent humans from making human errors. Now, of course, we can design our crypto systems in such a way that they're resistant against certain class of human errors or certain class of software bugs even, but not all, right? And also, it's reliable only if implemented correctly and used. These are obvious things in some way, but you will be surprised how many mistakes can happen in this transmission line between a theory paper that proves that some cryptographic construction is correct and an implementation of it, standardization of it, and this has in turn, a lot to do with the way we, the programming, that software systems are complex systems that involve a lot of actors and a lot of moving parts, and assumptions that are taken on a piece of paper, on a whiteboard, once you move them in computer system operation, they are not all equal. Some might be better than others, and so this is a complicated process where it's necessary. That's the only way to get things done. On the other hand, it's hard. People have made mistakes along the way. So you will see, have fun with it. I would, encourage you that this basically hopes to, hopefully will, expand your mental apparatus, and we'll show you that some beautiful things are possible. On the other hand, it will also teach you that this stuff is like dangerous to change, and small changes might have very dramatic consequences. So that said, I think we should move in and to first thing I wanted to talk, I always talk about in this class, is like some historical ciphers. And so they're all broken, but like it's kind of good to see why and how they're broken and what's at issue. Okay, before you jump into what's a secure, for example, one-time encryption. This is still chapter 1 in the textbook. So this is a picture we've seen. So a symmetric cipher, warhorse of cryptography, a pair of algorithms E and D. E to encrypt, given a plaintext and a key, you create a ciphertext. Decryption inverts that, and they act on the same key. We'll denote the key input in an algorithm often with this sign. And this no security by obscurity principle is called Kerckhoffs's principle, that algorithms are public spaces where messages, keys, and therefore ciphertext, all of these are known parameters. The only thing here in this example is that the secret is the choice of the key from a space. And clearly, the choice itself the space must be large so that brute force search is impossible, right? So let's see first designs where this principle is violated straight away. It's kind of good to see why. So a Caesar cipher. So it's really not a cipher because the key is public. The key is fixed to be 3. And but this is something that you can teach to small children. So the plaintext space is an alphabet or strings over the alphabet of, say, Latin from A to Z, although I guess in Latin there was no Y. And you shift by 3, so D is letter A shifted, right, by 3 in the alphabet. And E is B shifted 3 points down. Okay, so that's how you encrypt. And once you hit Z, then you have to wrap around, right? So it's really not the shift, but rotation. And you encrypt long sentence, right, a string over this alphabet by just applying this to every character in your message. And it's completely insecure because the key is public, right? So anybody who sees a ciphertext can decrypt it by just rotating every character back. Why was it used? Well, it was used against illiterate people, first of all, and it was used for people. It was an example of security by obscurity. If you didn't know that this code exists, you didn't know how to decrypt it. And shift cipher is a generalization where you shift by any shift, not just fixed shift 3, right? So you can, if you represent the alphabet as integers, mod 26, then you can represent, and the key is also an integer, mod 26. You can represent encryption as a summation mod 26 and decryption as subtracting a key. And what this really stands for, it's a shortcut, right? Because K is an integer mod 26, but M is not. M is a string over integers, each of which is a member of Z26. It's our notation for Z of n is integers between 0 and n-1. It's not our notation. That is the notation for modular arithmetic operations. So MIs are elements of Z26, so from 0 to 25. And when we say M plus K, we really mean MI, that CI, the ith element of the ciphertext, is computed as MI plus K, right? Mod 26 for every index I. So the same addition works on every element in the plaintext separately. Okay, so it's a shift cipher with a key, so Caesar cipher is a shift with K equal 3. And attack is obvious, right? Because this is such a small key space. Just brute force it, attempt to decrypt, and see whether the decryption is, whatever the assumption about the message space, right? These were XML messages. Okay, so check which one is a valid XML message, etc. Here's a generalization: substitution cipher. So rather than the key in a shift cipher was a certain class of permutations. This was a permutation that was a rotation by a fixed shift. So there was only 26 such permutations. In general, a key can be any permutation, right? So what's a permutation on this space? Each of these letters is like a number, right? This is a 0, this is 25. 0 went to 2, okay, and 1 went to, I guess that's a 24 or 23, right? Etc. So how much space do I need to write a permutation? Not that much. One character, it's a list of characters in this, and I only need 26 characters, right? So I can write down a permutation quite succinctly. And here is how I use it, right? So if this is my permutation and this is my plain text, again, the permutation acts character by character, just like the shift did. So it's not about permuting these things. It's about applying the permutation to each of the characters separately. So permutation is a permutation of Z26. I apply it to B. What does it mean? I just look at what the permutation outputs when on input B. Well, it outputs W. So W is my first ciphertext character. Then I look at the permutation acting on a second character. Well, it maps it to N. So N is my second ciphertext character, etc. Decryption applies the same procedure, looking at the inverse of this permutation, right? So every permutation implies its inverse, right? That's what it means. It's a permutation. It's 1 on 1 and on 2, so it's invertible. So I can, inefficiently look up where A is when I have an A and I need to invert it, or I just write down, first of all, preprocess, right? And I create the permutations that is an inverse of this one and just run the same code, but using this inverse permutation. So how hard is this to brute force? So if I have 26 letters in the alphabet, and the key space includes all permutations on 26 letters, how many permutations of 26 characters are there? And yeah, sorry, so I don't have like a, I guess I should do it on the chat. So I'll cut to the chase. It's this many, right? Because look, the permutation is fully described by this column. This column is a permutation of alphabet, right? I start with C, then I have a W, then I have N. This column is all letters permuted. And equally, this is 1-to-1. Every permutation of 26 letters will determine this column, and therefore will determine this function, right? So how many functions like that there are? Well, as many as permutations of 26 characters. So it's this. So 26 factorial is like 2 to 88. And that's actually a large number, right? So perhaps modern computer can be, can do 2 to the 30 operations in a second. I don't remember, maybe it's 2 to the 35 now, right? And so I have 1,000 computers, so now they're capable of doing 2 to the 45 in a second. So, okay, so I multiply by the number of seconds in a year, which I don't remember what it was, but like, let's say it's 2 to the 15 or 2 to the 20 even. So from 2 to the 45, I went to the 265. And it's still the probability that I hit this permutation is 2 to the 88 divided by 2 to the 65, vice versa, right? So it's 65 minus 88, it's 23. So it's 2 to the minus 23. That's less than 1 in a million, right? So it's 1 in 8 million. So not, I had 1,000 computers. They worked continuously for a year each. And still my chance of hitting this is only 1 in 8 million, no? So not very good for me. But it's irrelevant because substitution cipher is completely insecure. There's basically much faster attacks than this. And let's look at an attack example. So if you knew that the underlying plaintext space is English text, so then you can assume that a random, English sentence is basically correlated with in the frequency of letters as a random English sentence would be. So there is certain expected frequency of letters. E is the most frequent letter in the English alphabet. And when you look at the English sentences, English words in the dictionary, English whatever, right? These frequencies will maybe slightly fluctuate if you look at like medical texts and legal texts, or New York Times articles versus science articles. But actually, there is no reason to believe that these would be any different for those. So, and also you can look at so-called diagrams, right? So pairs of letters frequencies. And I'm talking about a so-called ciphertext only attack. So I see an output of a substitution cipher, permutation cipher on a long enough text. I see alphabet letters, and I will be able to decide what the corresponding plaintext was from this frequency information. So this frequency of information is freely available. You can look at web pages where actually even trigram or even 4 tuples frequencies are measured. So I look at the ciphertext that is long enough, and I will take information as follows: frequencies of occurrences of letters in the ciphertext, namely simply counts, and divided by how many, how long this thing was. So in this text, B occurred is the number 1 frequency letter. Then close after is N, U, P, etc. And now I have this table of most frequent letters in the English alphabet, freely available from, say, the web. And I just do a best match, right? So this is going to be my start. Let's assume that the most frequent one is E, is the most frequent one in the corresponds to. So this is a substitution cipher applied to E. And therefore, I have one line in this substitution cipher. I know that E went to B. Okay, I don't really know, but this is a good first assumption, right? And I fix other letters, like for example, perhaps N is the second, but maybe it's the next one, right? So I have some searches here. I'm going to, my first hypothesis will be that, of course, the first most frequent is E, the next frequent is T, and so forth. But this is a state of the search algorithm, because perhaps this first guess was wrong. Okay, so I have to modify my search algorithm accordingly. Second level of attack is that I can also look at the frequencies of diagrams. And it does show that certain diagrams have high frequency in here, NC. So I'm guessing that these frequent diagrams correspond to frequent diagrams in English language, like in, at. Now, this stuff has to be correlated with this stuff, right? So if I have guessed that U is a T, then PU will be correlated with this one, and see with that one and not the other way around, right? So coding this attack, it's okay. Like, you have to think how to code this fast, but still it's clearly possible, right? And I might get information from looking at frequencies of trigrams. They're not random. This is a famous trigram in an English language, right? Like the, so ing, right? And already from this, I basically have already half the table. I mean, I have a big chunk of the table of permutation. So the rest, my search space now reduces to, if I get half the table in this way, then the rest will, like instead of 26 factorial, I have 13 factorial. 13 factorial is a much, much smaller number, right? It's probably like 2 to the 20 or so. So a much faster search on the remaining letters. Use frequency of English language, use frequency of diagrams, and just do the best match algorithm between the frequencies you observe in the ciphertext and the frequencies assumed on the English. Now, this was ciphertext only. We didn't need to, we only worked from a single ciphertext. It assumes that the text is English, but really it works on any language, right? Because any language is, it's not like a random encoding. It has structure. It has some repeats, and if you had a language that was like efficient encoding, right? Then that's precisely the notion of efficient encoding. A random thing from the language corresponds to a random bit string of sufficient size, right? But you can see that that's not what languages do. And finding maximally efficient encoding, is actually hard. You have to know a lot a priori about the distribution and that is never known, really, right? So this attack will work on any message space, right? Like whether the minute you know something about the distribution of these plain text, that there are IP addresses, so they have certain structure that you expect. The HTML messages, certain structure that you expect. You will be searching for the correlations that are appropriate for these structures. So one takeaway is that sufficient key space, 2 to the 88 size, is not a guarantee of security by any means. It's a necessary requirement, but it's not a sufficient one. Here is another cipher, Vignere cipher, and shift ciphers that are working in parallel, if you will. So instead of a single shift, I have n, and I apply them to every nth letter of the plain text. In other words, ith letter in this plain text I will use the ith key, and also n plus ith, and also 2n plus ith. So it works in a cycle. It's easier to see, in a picture. Here's your plain text. Here is the key. This is 6 shifts. This K1, K2, K3, K4, K5, K6. Each of them a number, mod 26, telling you what the rotation of alphabets. So let's just copy this, because that's how we would work cyclically. So this is the 7th letter. For it, I will use the first key, so 1 plus 6. The second letter, I will use key 2 plus 6, etc. Okay, and then I just do mod 1 plus mod 26, because that's how shift cipher works. I take a number here and a number here, and I add them mod 26. That's shift cipher in operation, right? And now, yes, I increased the key space, but still, basically, I'm going to cryptanalyze it by looking at every sixth character and noticing that on those characters, it was a single key, K1, that acted. So, for example, if I basically it's n instances of shift cipher, and if I only look at frequencies of letters, then I will look at every sixth character in the ciphertext and measure frequency of those, right? So just isolate them and look at the frequencies, and then use the previous attack, correlate the most frequent with E, the second with T, etc. Now, perhaps you're wrong because a random sample of might not exactly have these frequencies you expect. But so modify the search space. I mean, you have to do a walk through that space, right? And do the same for every second letter. And then maybe correlate. Correlating, right? Like look at the diagrams. You couldn't use frequencies of diagrams by themselves in here, right? Because this, this does not correspond to two subsequent letters. But you can use diagrams to correlate the search for K2 with the search for K1. Yeah, so the code is going to be more complex. You can like easily have like a cool, software competition for who codes this most efficiently, and basically who can break these things with the least length. Okay, because the longer the stuff is, the more information you have, so the easier, the faster the search, right? But it's still the same attacks will work in principle. Now, modern ciphers. So why these primitive ciphers? So right, so because they were people were able to execute them with a pen and paper. Yeah, they could write a code name, and then whenever they wrote what it is they wanted to send, they could write it in this way and apply the cipher sort of in the head, or seeing the alphabet letters written somewhere and right to aid. But modern ciphers are not limited by this, right? So we can these traditional ciphers, which are limited to shifts, substitutions, we can do arbitrary computation, much more complex. In between these classic ciphers and us now, there were mechanical designs like Enigma, right? Which basically they were not fully, general computing machines, but they were limited by, beautiful technological designs that could work, with the technology of 1930s or 1920s. So rotating disks and electric signals that would be transcribed, as the electricity passes. This sort of changing wiring that is determined by position of one disk with relation to another, just hand waving the whole thing. And that gave another set of basically limitations, but yet it kind of expanded the possible crypto systems from those pen and paper shifts and substitutions ones, right? Analyzing them was highly non-trivial, but yet famously doable, right? Already with the computing machinery of the time, right? So and it gave a huge, kickstart for an impulse for advances in computing technology in general. And also people who did it, like Alan Turing, right, was basically created like a foundation for computer science in general, and for like what can and what cannot be done. and it was, in a sense, cryptography was the initial impulse for all of that. So yes, so rather than just substitutions and shifts, we have much more operations that we can do, and a type of right speeds and mechanics that were impossible for pen and paper, or for mixed mechanical electrical systems like Enigma. So let's stop here, and on Wednesday we'll jump to chapter 2. We'll look at basic notions of what's the privacy of communication, of encryption, security of encryption. We'll look at one-time pad, a very basic sort of beautiful principle, and yet we'll see limitations of it and what needs to happen so that we can go over these limitations as well. Okay, I will stop recording, and